Hey guys, so before we get into the actual content of today's lesson, one thing I wanted to preface by saying is that Dr. Moore sent me a message on Slack earlier today saying that he found an issue with one of the test cases for the second midterm and that he's currently trying to correct that test case. Once he makes that modification, I'm going to rerun the auto grader for all students and I will re-upload the grades to Avenue. Yeah, so sorry about that inconvenience. I found out about that earlier today, and I will need to run the auto grader again so that your test is marked against the correct test case. So Dr. Moore did not specify which test case had this issue, so I can't relay that information to you. But he did say he'd get it resolved fairly soon, so hopefully your mark should be updated soon. If you sent me an email asking about if you had like an issue with a certain test case, I will respond to it soon, but I'm still waiting on Dr. Moore to find out more details about this issue. And once I get those details, I will relay the information to you. However, I imagine that Dr. Moore himself will will probably notify students via Avenue in addition. Okay, cool. So with that out of the way, let me just say, first of all, good job once again with test 2. The marks are still pretty high. I don't think they were as high as the last one, but compared to the general average, they still, you guys did a good job, so nice work. Yeah, from a grades metric, the course is doing better than last semester, albeit it's online, so I don't know if it's an apt comparison. That being said, today's content, I think, is pretty relevant and pretty interesting. So I'm going to open up these slides that I linked on Avenue, and I wanted to make sure that I linked these slides because there are quite a few. So you might want to have them on your own monitor for your personal reference. But yeah, so today's topic is on trees. So a tree in computer science is another very common data structure, just like lists or dictionaries. A tree is just another way to store data. But what makes trees special is they have a hierarchy. You see in a list or in a string, for example, all of the elements are just in a series, one after another. But in a tree, each element has a specific relationship to other elements. Each element, or in a tree, elements are referred to as nodes, have a parent-child relationship. And we'll talk more about that in the next few slides. So if we take a look at the example in slide 3, we have a computer science tree data structure. So we have several elements or nodes in this data structure. I believe we have 6 in total. Awesome. And as you can see, each node of the tree can have multiple children. So children are just the nodes connected directly below. However, keep in mind that each of the nodes can only have one parent. All right, so in a tree data structure, nodes can have multiple children, but they can only have one parent. That is the essence of a tree. If a node has more than one parent, then it's not a tree. Now, keep in mind with B, this node has 3 children, C, D, and E. So C, D, and E are considered children nodes or child nodes of B, and B is considered the parent node of C, D, and E. Now, nodes do not have to have children. For example, B has no children, F has no children. F is only the child of A, but F itself is the parent to no other nodes. The node at the, right, so just to go over this again in more detail. So if we take a look at our tree data structure, we have B, and B is what we can call a parent node. Now, B is the parent node for C, D, and E, and C, D, and E are all children of B. Now, once again, in a tree data structure, every node does not have to have more children. C, D, E, F all of them have no children. All of them are not parents. They are themselves just other child nodes. Now, the node at the very top of the tree is called the root node. So this is just some terminology that I'll be using throughout today's lesson. Now, another property of trees is called depth. Depth is just the number of layers in a tree. So, for example, we have our first layer, layer 0, at the root node, and then A has 2 children, B and F, that they're on layer 1, and then B has 3 children on layer 2. So the max depth of this tree is 2. And just to reiterate, we have node B on layer 1 and C, D, and E on layer 2. So this is the general concept of a tree. The key thing to keep in mind is that in a tree data structure, every node can have multiple children, but it can only have one parent. For the scope of this class, if a node has more than one parent, it's not a tree. Now, in a binary tree, this is a bit more of a defined definition, because now every single parent can have at most 2 children. Previously, trees can have as many children as they like, but now every single node can have at most 2 children. And that brings us to the main topic of today, and that is the binary search tree. So in a binary search tree, all of the nodes have distinct values. And that makes a binary search tree a very special and a very useful tree, because this type of tree is really easy to transverse. And it's really easy to search the binary tree data structure. In today's lesson, we're going to be talking how to make this type of data structure in Python and how we can transverse this data structure in Python. But let's first just go over this example in some more detail. So in a binary search tree, each of the nodes can once again only have at most 2 children. They can have 1 child, as in the case of 14, but at most they can have 2 children. And of course, they can only have 1 parent still. So you'll notice that if a child node is less than the parent node, it'll be on the left branch. And if the child node is greater than the parent node, then it is on the right branch. Right? So for example, 8 has 2 children, 3 and 10. Because 3 is less than 8, it's on the left branch. And because 3 is greater than 8, it's on the right branch. Another aspect of the binary search tree is that all nodes or elements are distinct. So that means that no child node is going to have the same value as any other node. So for example, all of the values here you see in this tree are distinct. And that ensures that we can organize the data structure as need be, and that a child node is never going to equal to any other node, including its parent. Okay, cool. So let's try to go through an example of how we would develop this binary search tree. But just to ensure we get this concept, let's look at more detail at this binary search tree. So once again, each, like any other tree, all of the nodes can only have 1 parent. However, in a binary search tree, all of the nodes can only have at most 2 children. And all of the values in the tree are distinct. Now keep in mind, if a child is less than the value of the parent, it'll be on the left branch of that section of the tree. And if a child is greater than the parent, it'll be on the right branch. And you know the child will never equal the parent because it's a binary search tree and all values are distinct. All right, let's take a look at 3, for example. So with 3 being the parent node, 3 has 2 children, 1 and 6. 1 is on the left side because 1 is less than 3. 6 is on the right side because 6 is greater than 3. Okay, let's take a look at an example of how a binary search tree would be constructed in Python. So let's say, for example, we have the numbers 8, 3, 10, 1, and 6, and we wanted to organize these numbers into a binary search tree data structure. Well, let's go through these one by one. So first, we put the 8 up as our root node, and the next number we would assess is the 3. Well, 3 is less than 8, so should 3 be on the left side or right side of 8? It should be on the left side. Okay, and then we look at the next number, 10. So 10 is going to be greater than 8, so it should be on the right side of 8. And then next we have 1. So now we're still going to start looking from the root node, right? So I'm going to say 1. 1 is less than 8, so then we look at the left branch, but that's already occupied, so we perform the same analysis again. So 1 is less than 3, so 1 should be on the left branch as well. And finally, with the last number, we once again do the exact same operation that we did for all of the previous numbers. First, I look at the root node, and I know that 6 is less than 8, so it should be on the left branch. And then once again, because that branch is taken, I have to do the exact same comparison. So because 6 is greater than 3, it should be on the right branch. There we go. And that's how we would construct a binary search tree algorithmically given a sequence of numbers. And this is the key difference between things like binary search trees or trees and linked lists in comparison to other data structures like general strings and lists. Because in those data structures, all of the data is just in a sequence, one after another. But with trees and other linked data structures, there is a connection, a relationship between all of the data. Cool. Now, I imagine you guys may have some understanding now about how a binary search tree can be useful. It's useful specifically with searching. Because all the data is organized in the sequential way, where less than values are on the left side and greater than values are on the right side, it's very easy to bisect the tree into sections. And that makes it very easy then to search for specific values in a tree. Because I can look at each node one at a time, and by looking at just that node, I can know in which half of the tree the element I am trying to find is in. Now let's go through a quick example of how a searching algorithm would look like in a binary search tree. So let's suppose I have the same binary search tree. I'm given this data structure, and my task is to find the number 6. So what I would do is I would start at the root node. I would look first at the root node, and I would see, is the value I'm searching for 6, is that greater than or less than the root node? So because 6 is less than 8, I know that this value in the tree must be in the left-hand side of the tree. And just like that, I've cut off part of the tree. And then I can do the exact same operation again. So once again, I would consider, I'm looking for 6. The next node I'm looking at is 3. So because 6 is greater than 3, I know that 6 must then be in the come from the right branch off this node. And that's how I can get to the number 6. All right, there we go. So that's kind of a quick crash course in the binary search tree. I imagine picking up a cursory understanding of how trees work is fairly easy. But what you might be struggling with is why this is useful to us. Why would we want to make a tree data structure in Python? Hopefully, when we now actually build this data structure in Python, you might find it useful for why you may need a tree class in Python. So our task for today is we have to use object-oriented programming to make a binary search tree data structure. So we have to make a class that will make this data structure. So we need to implement the same object-oriented programming techniques that we learned on Monday. So our program is going to need to have some functions too. It's going to have the constructor to actually make the tree. And in addition to that, we're going to have some other functions that will do some operations like searching for a specific value in the tree and returning true or false if that value is in the tree. We'll also add an insert function to add more nodes or elements to our tree after we've constructed it. And finally, we'll have a depth function. And what the depth function will do is that it will return the max depth of the tree. And so we're actually going to have our tree make the exact same data structure, organize the exact same data that we did in our example. So before we start coding, I want to preface by saying that there is a correct standard way on how to make a binary search tree. The general technique is to make a program that has two classes, a node class and a tree class. And these two classes work together to create the binary search tree data structure. In fact, if you look at the YouTube description, I've linked the classic example of how this data structure should look like. The thing is, to implement that type of data structure, we need to use a concept called helper methods, which I think at this point in the course, not everyone may be totally comfortable with. So instead, I'm going to be implementing a binary search tree in a more, I would say maybe not the most elegant method, but definitely a more easier method. And with that, it might be easier for us to actually fulfill the objective of the class, which is to understand how tree data structures, or how any data structure where elements have a relationship, work. But if you want to see a better example, you can actually check out the YouTube description to see that. Or you can also see the example that Dr. Moore made, which is also another way of making the binary search tree. Okay, so with that in mind, I actually think I will, I'll get us started together in terms of making this binary search tree, because it might be a bit tough to attempt on your own. But if you want to pause the video, you totally can. But I'll start making it with you guys, then maybe I'll pause midway through if you guys want to take some initiative in getting it done. Okay, so once again, when making a tree, let me close these. So when I have to make my Python program, I will launch the idle shell to complete today's challenge. And once again, today's challenge is to make a Python program that creates the binary search tree. And we're going to be making this data structure with object-oriented programming. So I'm going to make a new Python program. And in order to make the binary search tree, I'll have to make a class to actually define what a tree or what a node is. Okay, so I'm just going to save this file. And I will save this file accordingly. And I'll save it as just BST, binary search tree. There we go. I guess maybe it should be capital because we're making a class, but that Python naming convention doesn't matter too much. Okay, so once again, we're going to be using our object-oriented programming knowledge to make this tree. So in order to make the binary search tree, the first thing we have to do is make a new class. So the initial header line of a class is just class, followed by the class name. So I'm going to make a class called node. And each of the instances of this class will be one of the nodes in our binary search tree. And of course, the first method inside the class has to be the init method or the constructor. So I'm going to write def, 2 underscores init, 2 underscores, and then I'm going to pass in my parameters. So I'm going to write self, followed by value. So self allows the object to refer to itself, and value will represent what the value of that node is. And then I will just define these values. Self.value is equal to value. So, and then I will say that each of the nodes also have two properties. Self.left underscore child and self.right_child. By default, I will set these properties to none. However, later on in my code, I'm going to make methods that allow us to define the left child and right child of each node. And those left and right childs themselves will be other instances of the node class. Now, the last thing I want to add is I'm going to say that value has a default value or default equivalence of none. So this allows me that if I don't pass in any value when making my node object, Python is going to assume the value is none. Okay, I'm going to pause here for a second, just see if there are any comments or anything. Hi, when do you think the marks are going to be updated? Yeah, so I'm not too sure, Reza. Dr. Moore said today that he's resolving the issue. He's working really hard to get that done. But yeah, as soon as he can resolve or fix the that test case, I'll rerun the autograder and re-upload it. He said he was going to work on it tonight, but yeah, as soon as I can't give us a hard deadline, but I would imagine within a few days. But yeah, if you have a specific qualm or issue with test 2 that you think is like of urgent concern, you totally can email me. But I will caution you that because I have to run the autograder again, that your mark should change accordingly if there was an issue with anything. However, I didn't get that many students who emailed me about the issue relatively when there's an issue with the test case. So I'm a bit surprised that there was any issue at all, because normally many more students have a concern or something. So I think maybe like a lot of students had an issue with the question already, and like they wouldn't have got the marks otherwise. But yeah, so it should be within a few days at most, Reza. Yeah, sorry about that. Okay. All right, so then I'm going to set another method in the node class, and that method is called def set value. And with this method, it's just a regular setter method that allows us to define what the value of that node element is. And I imagine you guys can figure out how this method should look like, right? We have our two parameters, self and value, and we're just going to say that self.value is equal to value, the classic Python setter method that we learned in last Monday's tutorial. Cool. And that is the bare bones of how the node class should look like. So the node class should have the set value method to allow us to set the value of the node. And each object in the node class should have three properties: its own value, and then its left and right child values. And later on, we're going to add some methods to set these values too. All right. Cool. I'm just going to pause here for a second, and then we can continue working on it. And I think the way I'll break this up today is I'll let you guys make the setters for left and right child, and then I'll show you at the end how you can get that done. Just as a way to give you guys more chance for initiative. Okay, cool. So next step we're going to make, so we've made our general data structure for node, where we have our constructor, and each object in this class is going to have the value as one of its properties, and also as the other two properties, the left child and right child. And keep in mind, left child and right child themselves will also be other instances of the node class. So we have nodes connected to nodes. So the next step was we had to make some other functions in our program. So these functions I'm going to write outside of the class. Normally it's written in another class, but that's going to add some more complexity that I think is we don't need to deal with. So I'm going to make a function called def insert. And what the insert function does is it correctly inserts a node into a tree, or it connects two nodes together. And we're going to be connecting nodes by saying that the left or right child of a node is equal to some other node. And that's how the nodes will have a relationship with each other. So let's make that def insert method. So I'm going to say def insert, and I'm going to say we're going to insert some node with some value. Cool. And we'll be calling this function to when we're given some root node that we can pass in, and then some value to add into that node as well. So node will be the root node that we're passing in, and value is the value of the new node that will be inserting correctly into the tree. And I'm just going to have an if statement initially saying that if node dot value is none. So notice how I'm not using a getter method to get the value. That's something you guys can add later on if you like, as a way of getting some individual experience writing this code. But yeah, so I can say if node.value is none, node.set value just as whatever value we're passing in. So what this method is saying is that if our root node has no defined value, if it's just one node by itself with no children or anything like that yet, then just make the value equal directly to that node. Otherwise, if node does have a value, we're going to see if our new value is less than or greater than node. If it's less than, then the new value should go on the left-hand side of node. If it's greater than, the new value should go on the right-hand side of node. So I'm going to say else if value is less than node.value. And keep in mind, I'm calling these as properties right now, but what you guys can do to add some complexity is make getter methods to call these values instead. And I can say if node.left underscore child is none, then all I have to do is make it equal to node.left underscore child. That's equal to node value. There we go. So essentially what I'm doing is I'm saying that if the value of our root node, if our new value is less than that value, then we know the new value has to go on the left child. It has to go on the left branch. And so all we're doing is we're going to make a new node object that is also equal to the left child. However, there may already be a node there. Left child may already be defined, in which case we have to do the exact same operation again, the exact same comparison now on the left child. So what technique should we use to get that done? Any ideas? What concept can we use? Recursion, right? So I can say if the child is already defined, we have to do the exact same insertion comparison once again. And I can just say insert node.left underscore child and value. And we're going to call the exact same function, but now we're looking at the tree from this left child, from starting from the left child. Just to give you an example, so initially we were looking at the tree from the very root. However, if we realize that the left child is defined, we have to do the exact same comparison again. And so we're going to call the insert function once again, but this time looking at it from the left child directly. Okay, cool. And then I can do the exact same logic for the right node. So if value is greater than, so if the new value is greater than the current parent node value, then we have to do the exact same comparison, this time on the right side. So once again, then we would just define the right child as being the node value. Oh, sorry, it is none, I bet. And else, we have to do the exact same comparison again, but this time with the right child. So I can just copy this actually to save some time. Cool. All right, and that is pretty much the insertion function. So how it's going to work is we're given some root node and a new value that we're adding in. And if the root node has no value, if it's either the bottom of the tree or it's like the first time we're adding a value, then we're just going to set node to be equal to that value. Otherwise, if the new value is less than the root node, we're going to look at the try to add it in on the left-hand side. And if it's greater than the root node, we're going to add in the value on the right-hand side. So have we considered all of the possibilities for what can happen in this if-else tree? So we have a condition if node value is equal to none, or if the value is less than node value or greater than node value. Is there a final condition we should think about? Yeah, so ideally in a binary search tree, all of the values should be distinct. However, under some circumstances, maybe they'll pass in by accident a value twice. And in that case, we can just print something to the command line saying, like, print, this value is already in the tree. In which case, we wouldn't want to add it in again, because all values in a binary search tree are distinct or unique. Cool, and that's the first method. All right, so we can try it out actually, just to ensure it works the way we want it to. So I can just call, I guess we could make a for loop to call them to iterate through an entire list. But instead, what we can just do is we can define our root node. You can see that's equal to node. And keep in mind, because I'm passing in no parameter for the value, the default value is set to none. And then I can just add in a bunch of elements one at a time. So how did we add them in? So I think the sequence was, it was on the left side. Yeah, okay, I think, so here's the sequence. So I can just then say insert into my root node 8, and then 3, and all these other values. 3, 10, 1, 6, 7. Cool. All right then. Awesome. And so there we have our insert function, and we have the init function for the class. I'll just take a quick look and try to avoid spelling mistakes and such. Those are going to cause problems. Yeah, I think we should be good. Okay, so then you can try this out in order to make our tree class, and so I can run the code. Cool, and then it executes fine. And then I can verify that my data structure works the way I want it to by just, for now, calling the elements of the root node, right? So what I can do is I can just print out the elements one at a time. So if I, for example, print the root underscore node dot value, what should that return? Should return 8, right? But then if I look at the, let me split screen this actually. So yeah, so then if I call, for example, the left child of the root node, so if we look at root node dot left underscore child dot value, and then if I run this code again, we're going to look at 8, and then 8's left child, which is 3, and we'll get that value back. There we go. And so I can use this technique just to print out the elements one at a time and ensure that the data structure was made correctly. Okay, so let's make the next function, which was the find method. And what the find method does is it just prints out the, it returns true or false if an element is in the tree. So not that bad, it's relatively easy to make. So all I'm going to do is I'll make a new method and I'll call it, I think it's set search in the doc. So I'll say def search. And once again, I'll have two parameters in this function, the node, which will be the root node that we're passing in, and the value that we're looking for. And it's a pretty simple logic. So I'm just going to start off by seeing if the root node has the value that we're looking for. And if it is, then I would return true because that value exists in the tree. Otherwise, I would then perform the same operation either on the left branch or the right branch. So if the value is less than the node, then I know if the value does exist in the tree, it'll be in the left branch. So I'll say else if node dot the value is less than node dot value, well then I know that the value must exist in the left side of the tree. So I'll call the function again, and this time I'll start looking from the left child. And I'm looking at the same value once again. And same idea for the right child. And if none of these conditions are true, I would just return false then. And I'm just putting the false in an else statement just to highlight the conditions. One thing to keep in mind is that when we're calling the left child or right child, those values may be none, in which case we can't do this property comparison. So I'm just going to have another encapsulating if statement saying if node. So if the node is defined, we will check to see if the node's value is equal to our searching value. And if it's not defined, well, then we know that that node cannot contain the value, and we'd be at the end of the tree then, so we can return false. Cool. All right, so not too bad. So we can test this code out too. So after we've made our tree, so we fully made our tree here, we can just call the find function. So I can say print find, and if I try to find 6, starting from the root node, it should return true. Oh, sorry, search. I called it something else earlier on in my notes. Search. There we go, true. If I try to pass the number that doesn't exist, I would get an error. Right, and that's the find method. Okay, the last method is we have to make the last function, because these are outside the class, is we have to make a function to return the depth of the tree. So that's not too bad either. So I'm going to make a new function called depth, and once again, this will have just one property this time, which is just the node that we're starting to measure the depth from. And there are a couple of ways we can do this. I think, should we do it recursively? Okay, let's do it recursively. So I can say if node dot left underscore child. So I can look at my node and I can see whether the left child and right child have values if they're defined. And if they are defined, then I can continue measuring the depth. So I can say if there is no left child, and that means that surely the max depth in the left direction must be 0, because you can go no further down the tree. And else, we will increment 1 to left max, but with some recursion, right? I'll say left max is equal to depth dot left underscore child, depth node dot left underscore child and then +1. And so that will just get the max depth going from the left direction. And then I can do the same thing in the right direction. Oh, sorry, this should be not tabbed. Beautiful. And then we'll have the max depth in either direction, and we can just return that value. I'll use the max function just to save time. Return max of left underscore max and right underscore max. All right, that wasn't too bad. And we can test out this function as well. Just with a simple call. And my apologies for taking the initiative here. I just thought this would be a bit of a tough task to take on independently. But I promise I'll give you some time to pursue this independently right after with some additional stuff you can get done. Okay, and just going to make a call to the function, verify it works. And I think we specified what the depth was earlier on. But, oh, shoot. So we're starting from 3 in this case. But, yeah, so there are like 3 layers to the to it in total. I guess you start counting from 1. All right. How can we correct that then? Because that's bad form. Cool. Okay, so that's not ideal, but I hope the point is still illustrated. Any other questions or queries? Okay, cool. So that was the last function. I guess we can just -1 from the end, but that's not the most elegant solution. But I guess that would work too, because we're adding on too much. Or actually, how would it? Oh, is it because of the 7 that's changing the tree? So my apologies. Let me just take a look at. So we have 8, 3. Oh, I think I added an extra element to that. Okay, that makes more sense. I was a bit confused there for a second. So let's run this again. There we go. Okay, yeah. So my apologies. I added an extra element to the tree. Cool, cool. Okay, so in terms of, so we've made our class here that defines the node, and we have these other functions that allow us to insert values to the node, search for a value in the node, and get the max depth of the node. And yeah, my apologies. I wasn't looking at the same tree. I had an extra node there, which increased the depth. And we can verify that our node works as need be by calling the properties, but that's not ideal. So if you guys want to do an individual task or take some initiative, if you want, you can change this code so that instead of us calling the properties of the object throughout the code, you can make the getter and setter methods. So we'd make get value, get right child, get left child. So that can be a task you can work on to get it done individually. And you can refer to Monday's lesson on object-oriented programming to get more details on making that code. All right. So are there any additional questions about today's class? I don't see any. I guess it's a good sign. Yeah, so I hope everything's going well, and we will run the auto grader again soon. I'm trying to find that out too from Dr. Moore. But it should be soon, ideally. Cool, cool. Okay, so I will leave this code up, and I'll leave it up by making the text a bit smaller so you can see it all at once. Where is that? Or I think I actually linked it in the YouTube channel. Let me just check that out. Sorry. Yeah, so we're in the it's in the YouTube channel. There we go. So you can look at the code there in terms of copying it and such. And in terms of the next step, what I would do is I would try to replace the call to properties to getter and setter methods. So you guys can try that out on your own. And yeah, if you have any issues, you can email me. I'll probably respond to all today's emails in the morning tomorrow. There are a couple of things I have to get done first. Yeah, but if there are no questions, that's all for today's lesson. And we should be good to go. All right, cool, cool. And so once again, there is generally in actuality, making a binary search tree, you would have these methods in a separate class. But in order to get that done, you need to use helper methods, which may be an abstract concept. So we did it this way instead. But if you're looking at how that can also be done, I've linked a better example of binary search trees in the description, and you can check that out just to supplement your understanding. All right, so if there are no additional questions, I'm going to log off for the day. So I'll just check the thing once again, and yeah, it seems empty to me. All right, guys, so yeah, have a good weekend, and yeah, I hope we will run the auto grader again soon, and let us know if you have any issues or concerns. All right, take care, guys. Bye.